Welcome back to the deep dive. This time we're going deeper than just algorithms.
Oh, yeah.
We're going to learn how to actually build them
Wow.
with model-based machine learning.
Okay.
And our guide for this deep dive is John Winn's model-based machine learning.
Sounds interesting.
It's really about thinking differently.
In what way?
Instead of just throwing data at a problem, we're going to become AI architects.
I
We have to think about the hidden assumptions, right?
Right, exactly.
Model-based machine learning brings those assumptions into the open.
It does.
Which not only gives us more control over our solutions, but also helps us adapt to new situations. Transparency. And a deeper understanding of why things work or don't.
Or don't, yeah.
To explain this, Winn starts with something completely unexpected.
What's that?
A murder mystery.
A murder mystery.
It's a brilliant way to ease us into some pretty complex probability concepts.
I like it already.
So picture this. A suspicious death. 2 suspects.
Okay.
Miss Auburn, 70% chance she's the culprit.
Okay.
And Major Gray,
All right.
our shady character.
Right.
And no good murder mystery is complete without weapons.
Of course not. What do we have?
A revolver
Okay. Classic.
and a dagger.
Ooh, interesting.
Now, if we assume Miss Auburn did it, there's only a 20% chance she used the revolver.
Okay.
But Major Gray,
Yeah.
let's just say he's a revolver kind of guy.
I gotcha.
But wait, there's more.
There's more.
It starts to rain.
What?
What does the weather have to do with anything?
Well, that's the point, isn't it?
It is.
Model-based machine learning helps us focus.
On the relevant factors,
Yeah.
the chance of rain is totally independent of our murder mystery.
Right. Separate.
It helps show how models can separate the signal from the noise.
Like a filter.
Now, Winn then introduces marginalization.
Marginalization.
It sounds kind of intimidating,
It does sound a little bit intimidating, yeah.
but it's actually very useful.
Oh, okay.
Think of it like zooming in on a specific piece of evidence.
All right.
So say we want to know the probability that A and Y suspect used a revolver.
Okay.
Regardless of who actually pulled the trigger,
Uh-huh.
marginalization lets us extract that probability
From all the other possibilities.
from all the other possibilities.
Yeah.
It's so valuable,
When you need to explain your reasoning, right?
especially in a complex situation. It helps you pinpoint what matters.
Pinpoint those key factors.
Now, as our murder mystery grows more complex, we need a better way to visualize all these relationships.
Of course.
And that's where factor graphs come in.
Factor graphs.
They're like a visual representation of our assumptions,
Uh-huh.
like a detective's board, but instead of photos and red string,
Yeah.
we have variables and connections.
I see.
And these factor graphs are preferred over Bayes nets
Because?
because they provide a more complete picture. It's like having all the pieces of the puzzle in one place.
All in one place.
Yeah.
Gotcha.
And one of the cool things about this is that it highlights conditional independence.
Okay.
So, for example, if we already know the murderer,
Yeah.
learning about the weapon they used doesn't tell us anything more about the weather.
They're separate. They're independent.
They're conditionally independent given the murderer.
Given the murderer, right.
So we can ignore irrelevant information.
Simplifies things.
Okay, so we've cracked the case.
We did it.
The book takes a sharp turn
Okay.
and now throws us into the world of skill assessment.
Skill assessment.
Imagine designing a test for software developers
Right.
focused on C# and SQL.
Okay.
The challenge is figuring out how to accurately measure someone's skills.
Uh-huh.
We need to account for lucky guesses, tricky questions,
Right. All the factors.
all the factors.
Yeah.
So to build this model, we need to start with some assumptions.
Okay. What are we assuming?
First, someone either has a skill or they don't.
All right.
It's a simplification, but a good starting point.
A good starting point.
We also assume that knowing C# scale doesn't tell us anything about SQL.
Okay.
And we also assume that if you don't know the answer, you'll guess randomly.
Sure enough.
And we also need to make sure the test itself is fair.
Absolutely.
No distractions, no unfair advantages.
A level playing field.
All of these assumptions are represented in the model.
They are.
And now, to connect those individual skills to the overall outcome, we need something called the AND factor.
AND factor.
So someone only passes if they have both HI, and D SQL skills.
Like a gatekeeper?
But even if someone has the skills, there's still a chance they make a mistake.
They could.
So we need what's called the noisy answer factor.
That's the answer. Okay.
It acknowledges that people aren't perfect.
Right. Experts can get things wrong sometimes.
Even experts can get tricked by a tough question.
Uh-huh.
Now, when we start crunching numbers to figure out how someone did,
Okay.
we run into something called products of distributions.
Products of distribution.
Lynn walks us through an example to make it clear.
Okay, good.
But as we add more questions, we run into a problem.
What's that?
Loopiness.
Loopiness.
It happens when the relationships between variables create a circular dependency.
It's a challenge for belief propagation.
Especially for belief propagation. It relies on messages traveling in one direction.
Right, one direction.
So it's like you need to know the answer before you even ask the question.
Kind of a paradox.
It is. But don't worry, there's a solution.
Oh, good.
Loopy belief propagation.
Loopy belief propagation.
A clever workaround. For complex models, it iteratively refines messages until they converge on a solution.
Right.
Might not be perfect, but it's a practical compromise.
For real-world complexity.
Because sometimes a good enough answer to the right question is more valuable
Than a perfect answer to the wrong one.
than a perfect answer to the wrong one.
Exactly. Pick your battles.
Pick your battles. Okay, so we've built our model, accounted for loopiness.
Uh-huh.
Now we need to make sure it works.
How do we do that?
Ancestral sampling.
Ancestral sampling.
Think of it like a simulation.
Okay.
We randomly generate skills and answers
Yeah.
based on the model's assumptions
Okay.
and compare it to the model's output.
If they align.
If they align, we can be more confident.
Good.
But when Winn tested this, he found something really interesting.
Oh.
The model predicted more incorrect answers than people actually gave.
Interesting.
It turned out the assumption about random guessing wasn't accurate.
People aren't always random.
Exactly. People can eliminate obviously wrong options
Mm.
or make educated guesses.
Makes sense.
Yeah, so back to the drawing board.
Well, not quite.
Not quite.
No.
Okay.
We can adapt.
Adapt the
I
model.
think that's right.
Instead of assuming random guessing, we can introduce question-specific guess probabilities.
Okay.
Some questions might be more guessable than others.
Uh-huh.
So we're adding complexity, but making it more realistic.
More realistic, yeah.
To represent the uncertainty in these guess probabilities, Winn introduces the beta distribution.
Beta distribution.
Allows us to express different levels of confidence in our guess probabilities.
Okay. Cool.
And the model can learn these guess probabilities right alongside the skills.
Simultaneously. Yeah.
Our factor graph gets more complex,
Ours.
with multiple plates to handle the data structure.
Right.
But the results are worth it.
They are.
We can see these guess probabilities vary across questions.
So it's working.
Some are definitely more guessable,
Yeah.
and we can measure this improvement.
Using.
Negative log probability.
Okay.
The lower, the better.
The lower, the better. Gotcha.
And incorporating guess probabilities leads to a significant boost in accuracy.
That's great.
And Winn doesn't stop there.
It keeps going.
He throws a bunch of performance metrics at us.
Okay. Like,
ROC curves, AUC, precision recall curves.
these are all different ways to look at performance.
They give us different perspectives.
On how well the model is doing.
Makes sense.
And then there's calibration.
Calibration.
Essentially checking if the model's confidence levels match reality.
Oh.
If it says 80% sure, it should be right 80% of the time.
Right.
This is crucial
Correct.
for making sure the model's predictions are reliable and trustworthy.
It's got to be reliable.
If it's poorly calibrated,
Yeah.
it means something's wrong with our assumptions or how we're training the model.
Gotcha. Back again for more model-based machine learning fun.
This time, we're diving into a topic near and dear to our hearts.
What's that?
Recommendations.
Recommendations.
Chapter 5 explores how those algorithms seem to know our tastes better than we do.
They can be pretty spooky sometimes.
Okay, but how do we actually build something that can do that?
Winn starts with a simple analogy. Imagine a line
A line.
representing movie preferences.
Okay.
Action blockbusters on one end and tear-jerking dramas on the other.
All right, so where do people fall on this line? We can place people based on their preferences.
Makes sense.
Someone who loves explosions would be closer to the action end, and someone who prefers emotional storylines would be on the drama side.
Okay. What about people who like both action and drama?
Good point. That's where neutrality comes in.
Neutrality.
If you enjoy both genres equally, you'd be in the middle.
So it's not just extremes.
It's about capturing those shades of gray.
I like it.
But to make things even more interesting,
More interesting.
we add another dimension.
Okay.
Escapist versus realistic movies.
Ooh, now we're talking.
Now we have a two-dimensional space.
To capture even more nuanced preferences.
Exactly.
So someone who loves action-packed escapist movies would be in a totally different area than someone who prefers, like, thought-provoking, realistic dramas.
Totally different.
Okay, we've got our movie map. But how do we place the movies themselves?
We use trait values.
Good trait values.
Each movie gets a value on each dimension.
So action drama.
And escapist realistic.
It's like giving each movie coordinates.
It is. We're plotting both people A and D movies in this space.
Cool. So how do we connect the dots, so to speak?
We use factor graphs.
Factor graphs.
To represent the relationships between users, movies, and their traits.
Each connection in the graph represents...
A relationship.
Okay.
Such as...
the user's affinity for a particular trait. Or a movie's strength in that trait.
But remember, we're working with probabilities here.
Always probabilities.
We're not saying someone definitely loves a certain genre.
Right. It's about capturing likelihood.
Based on their past choices and those movie characteristics.
Right.
So it's like a personalized probability map of taste.
Exactly.
Now, to train our model, we need data.
What kind of data?
The gold standard.
Oh.
Which is...
Lens.
Movie Lens, a classic.
It's a treasure trove of user ratings. But there's a catch, right?
There is. Moody Lens uses a 5-star system. And our model works with, like, dislike preferences.
Oh, right. So we need to translate those star ratings.
We do. For now, let's simplify.
How?
Ratings of 4 or above are likes.
And everything else?
A dislike.
Okay. A good starting point.
It is.
We'll explore more nuanced approaches later.
We will.
So we've got the data, translated the ratings. What happens next?
Expectation propagation.
Expectation propagation.
It helps infer the positions of users and movies.
In our trait space.
In our trait space, yes, based on the data.
So we're watching the model learn and adapt.
Exactly.
But as it learns, we might encounter something unexpected.
What's that?
Symmetries.
Symmetries.
In a movie recommendation system.
That seems odd.
It does. But symmetries are a common issue in probabilistic models.
How so?
It's when multiple configurations lead to the same observed data.
I see.
Like, imagine flipping the action drama axis.
Okay.
The model would still make the same predictions.
Even though the meaning is reversed.
Even though the meaning is reversed.
Yeah.
It's like the model can't decide which way is up.
Action could be left or right.
And it wouldn't know the difference.
Interesting. So how do we fix that?
We need to break the symmetry.
Break the symmetry.
We can add slight perturbations to the initial messages.
Like a little nudge.
Exactly. A gentle nudge in the right direction.
I see.
Winn does this by anchoring two movies.
Anchoring?
Let's say The Usual Suspects and Mulholland Drive.
Two very different movies.
Very different. We fix their positions on those axes.
Action drama and escaped realistic.
Exactly. To break the symmetry and provide a reference point.
Gotcha.
So what does our map look like now?
Imagine a scatter plot.
Go.
Each dot is a movie. Its position reflects those learned trait values.
So movies clustered together share similar characteristics.
They do, and those further apart are more distinct.
So clusters of action movies, rom-coms, sci-fi epics.
All organized based on their genre or feel.
Very cool. All right, time to generate some recommendations.
All right, how do we do that?
Find the closest movies to the user in trait space.
Makes sense, based on distance.
Exactly. The closer the movie, the higher the probability of a like.
Okay.
Winn evaluates this using the validation set.
Those held out ratings.
To see how well the predictions match reality.
How did it do?
The results are pretty good.
That's great.
Especially for users with well-defined tastes.
Makes sense. But there are limitations, right?
Always limitations.
Yeah.
One is missing data.
Missing data.
Not every user rates every movie.
Of course.
If we just assume those missing ratings are dislikes, it can create bias.
Right. It's like assuming someone hates all the books they haven't read.
Not very accurate. In reality, those missing ratings can mean a lot of things.
You can?
Maybe they haven't seen the movie. Or they just haven't gotten around to rating it.
Makes sense.
We need to account for this without making assumptions.
We do. That's what Chapter 6 tackles.
Missing data.
And its impact on accuracy.
Okay. But why the sudden jump to childhood asthma?
It might seem like a detour.
It does.
But the principles apply to a lot of things.
Like recommendations?
Especially recommendations.
Okay, I'm intrigued.
This chapter dives into a long-term study.
About?
Tracking children's sensitization to allergens.
Okay, so skin prick tests and blood tests.
Showing allergic reactions.
In a long-term study like that, I bet there's a lot of missing data.
There is, and Winn highlights how this can introduce bias.
If it's not handled carefully.
If it's not handled carefully.
Yeah, how so? Can you give an example?
Imagine a child who skips blood tests because they're afraid of needles.
Okay.
That missing data isn't random.
Right.
It's related to fear.
Which could be influencing their allergic reaction.
Exactly.
So the absence of data is telling us something important.
Very important. This is data not missing at random.
Not missing at random.
Right.
Okay.
The missingness is related to a factor.
Which is influencing the outcome.
Right. So how do we account for this?
Do we just throw out that data?
We can't. That would introduce more bias.
Oh, right. So
We need to model the missing data.
without making assumptions.
Right. It's like being a detective again.
We're investigating the missing data.
We are. To understand its impact.
So Winn outlines different types of missing data,
He does.
like missing completely at random
Pure chance.
or missing at random.
Related to observed factors.
So, like, if a child misses a test because they were on vacation.
That's missing at random, assuming the vacation wasn't influenced by their allergies.
Okay.
And then there's not missing at random,
Like our needle-phobic child.
where the missingness is related to something we don't see.
Okay. So the way we handle it depends on the type.
Exactly. For data missing at random, we can use imputation.
Imputation.
We fill in those values based on observed patterns. But for not missing at random,
Things get tricky.
things get trickier. We need more sophisticated models.
That can account for the potential bias.
Right. And here's the connection to recommendations.
Okay.
Missing ratings can be just as informative.
Someone who hasn't rated a movie might have specific reasons.
Right.
Maybe they avoid certain genres.
Or haven't had the chance to see it.
By modeling these missing ratings.
We capture more nuanced preferences.
And make better recommendations.
Exactly. It's like acknowledging that silence speaks volumes.
Now, Winn takes this further.
He does.
He introduces model selection.
Model selection.
Is that where we choose between different recommendation algorithms?
It's a broader concept.
Okay.
It's about comparing different models that explain the same data.
Okay. So it's like a competition
It is a competition between
to
models.
find the best explanation.
Exactly.
Winn uses the example of a randomized controlled trial
A classic.
for testing medical interventions.
Like a new drug.
Right. Let's say we're testing a drug.
Okay.
We want to compare two models.
Right.
One says the drug works, the other says it doesn't.
A head-to-head.
To figure out which is more likely, we need to quantify the evidence.
Right.
Winn introduces model evidence,
Model evidence.
also called marginal likelihood.
Marginal likelihood, yeah.
How do we calculate that?
We integrate over all possible values of the unobserved variables.
Integration, huh?
There are techniques to approximate it.
Like,
Expectation propagation.
it's everywhere.
It's quite useful. Once we have the model evidence, we compare them.
Using
The Bayes factor
the Bayes factor,
tells us which model is more likely,
given the data,
given the data.
like a scorecard.
Now, to visualize this, Winn uses gates.
Case.
They control the flow of information in the factor graph. It's
Okay.
like a switch between models,
Oh, I see.
between drug works and drug doesn't work,
So we can seamlessly switch between explanations.
and infer both the model parameters and the probability of each model.
It's streamlining model selection.
Exactly.
And this technique can be used for more than two models,
It can.
like in the asthma study.
We might compare models with different numbers of sensitization classes.
Right, those groups of children with similar allergy patterns.
We let the data guide us towards the best explanation.
It's like the data is voting.
It is.
And this applies to recommendations too.
In what way?
Imagine a system that considers multiple models simultaneously.
Oh, okay.
One using collaborative filtering,
Okay.
another using content-based filtering,
So different approaches.
working together.
In one system.
Using gates, the data determines the best model for a given user.
That's amazing.
So personalized recommendation strategy.
That adapts. I love it.
Okay, we've tackled missing data, mastered model selection.
What's next?
We're going to tap into the collective wisdom of the crowd.
The crowd.
Crowdsourcing.
Ah.
Chapter 7 explores how we can use this to improve our models.
Makes sense. Lots of potential there.
Winn uses the example of Ushahidi,
The Ushahidi.
a platform that emerged during the 2008 Kenyan election crisis.
Uh-huh.
They used crowdsourced reports to map incidents of violence.
Yeah.
This chapter explores how to leverage this for machine learning.
Like labeling data.
Exactly. Instead of relying on a few experts,
Right.
we can distribute the work to a crowd and combine their responses.
But not all crowd workers are created equal.
That's true. Some are more accurate than others.
More consistent.
Some might rush through the task.
Others might be super careful.
So we need a way to account for those individual differences.
We do.
And Winn's model does just that.
Really?
It accounts for the varying abilities and biases of crowd workers.
So it learns who to trust.
It's like a reputation system.
Cool. Can you give an example?
Imagine labeling tweets related to the Haiti earthquake.
Okay.
Crowd workers categorize them based on the type of information.
Requests for help, reports of damage.
Right. And the model learns which workers are more reliable for certain categories.
And which ones tend to make certain mistakes.
We're combining the wisdom of the crowd with the power of language analysis.
Wow.
Because the model also analyzes the words in the tweets.
So it's not just relying on the crowd's judgment.
Exactly. And the combined model achieves high accuracy in classifying the tweets.
That's amazing.
So we're integrating diverse information sources.
To improve our models.
And this has broad applications.
Like what?
Imagine using it to train models for image recognition or sentiment analysis.
The possibilities are endless.
They are. Okay, let's shift gears.
Hmm?
Uncovering hidden topics in text.
Interesting.
Ever heard of LDA?
LDA, latent Dirichlet allocation.
That's the one.
It sounds complicated.
It's a model for uncovering those hidden topics in a collection of documents.
So if we feed it a bunch of articles, it extracts the main topics.
Like a digital librarian.
That's a good analogy.
Organizing a vast library by theme.
I like it. So no predefined topics.
It learns them from the data.
Directly from the data.
Discovering the hidden structure.
That's powerful.
Can you give an example?
Imagine documents about computer science. LDA would group them into topics like algorithms, programming languages, or hardware.
Based on the words used.
Exactly. Documents mentioning sorting and complexity would fall under algorithms.
While those discussing Python or Java would be programming languages.
Exactly. Winn emphasizes understanding the assumptions, though.
Assumptions.
LDA assumes each document is a mixture of topics, and each word comes from one of those topics.
It's like a tapestry woven from threads of knowledge.
I like that. LDA helps unravel those threads.
So LDA is a tool for anyone working with a lot of text.
Researchers, journalists, analysts.
They could all benefit.
Now, as we move to the last chapter, Winn focuses on understanding and interpreting models.
Crucial. What good is a model if we don't know what it's saying?
Exactly. He starts by dissecting decision trees.
Oh, yeah, decision trees. Those are classic.
They're visually intuitive.
Like a flowchart for making decisions.
Winn points out the problem of hard decision boundaries.
Hard boundaries.
A small change in the input can completely change the prediction.
Right, because they're so strict.
To address this, he introduces decision forests.
Decision forests.
Ensembles of multiple trees.
Working together for a more robust prediction.
Like a committee.
Okay.
Next up, principal component analysis.
PCA.
It's a technique for dimensionality reduction.
Dimensionality reduction.
Finding the most important variations in a data set.
So if you have hundreds of features,
PCA identifies the few that really matter.
Simplifying without losing too much detail.
Exactly.
Can you give me an analogy for how PCA works?
Imagine a cloud of data points in 3D space.
Okay.
PCA finds the lines that best fit through that cloud.
Capturing the main directions of spread.
Like finding the axis of an ellipsoid?
Reducing complexity from 3D to 2D or even 1D.
But PCA has assumptions, of course.
It does.
It assumes the data is linear, and that the most important variations are those that maximize variance.
So if the data is nonlinear,
PCA might miss something.
we need to choose the right tool for the job.
We do.
Okay, what else does Winn dissect?
K means clustering.
K means...
For grouping data points into clusters.
It's like sorting socks by color.
It is. We want to group similar things together.
Like customers with similar buying habits.
Exactly. We could then target marketing more effectively.
But it also makes assumptions, right?
It assumes clusters are spherical.
Okay.
And have roughly the same size and density.
So if they're a weird shape or some are much bigger,
K-means might not work as well.
we need to be aware of those limitations.
Winn concludes with a powerful message.
What's that?
Understanding model assumptions isn't just about technical skill.
It's not.
It's about transparency,
Okay.
interpretability, fairness.
In machine learning.
It's about understanding why AI makes the decisions it does.
Especially as it influences our lives more and more.
Model-based ML helps us build trustworthy AI.
That benefits humanity. Wow, what a journey.
It's been quite an adventure.
We've explored so much.
Murder mysteries to crowdsourcing.
I have a new appreciation for model-based machine learning.
It's a powerful approach.
But how do we apply this to our own work?
That's a great question, and one we'll explore in the final part of our deep dive.
Welcome back to the deep dive. We've solved murder mysteries, navigated gaming tournaments, and even conquered email overload, all with model-based machine learning.
We have. It's been quite a ride.
But now for the big question.
Uh-oh, the big question. What's that?
How do we actually use all of this?
Right. It's one thing to understand the ideas, but another to put them into action.
So give us the roadmap. Where do we even begin?
Well, the first step is finding the right problem. Model-based machine learning is really powerful when you're dealing with uncertainty and complex relationships.
So it's not just predicting an outcome. It's about understanding the whole system, the factors involved, how they all connect.
Exactly. Think less about will this customer click on the ad and more about what drives purchasing decisions.
It's about building a model that captures the essence of the problem, not just the surface stuff.
That's it. And once you've got the problem, got to define your goals. What are you trying to achieve?
Right, because the goal shapes the model. Are we building a recommendation engine, a fraud detector, a medical diagnosis tool?
Each application has its own demands, and that means a different approach.
And let's not forget about assumptions. Winn is really big on making those explicit.
Oh, absolutely. You have to lay out your cards on the table. You're being transparent about what the model can and can't do.
We're not pretending it's perfect.
Yeah.
Okay, so we have our problem, goals, thought about assumptions. What's next? Time to choose our weapons.
More like our tools. Luckily, there's a whole arsenal out there for building these models.
Lay it on me.
Well, Winn mentions some fantastic frameworks like Infer.net, Stan, PyMC3.
Those names sound familiar.
They're probabilistic programming languages, specifically for this kind of model.
So instead of regular code, it's a language that gets probability.
Exactly. They do the heavy lifting, let you focus on the model structure and your assumptions.
Like having a team of mathematicians on call. What if you're more visual?
There are graphical modeling tools for that. Connect nodes, represent variables, just like our detectives board.
But now we're solving data mysteries. So once the model's built, time to train it, right?
Gotta feed it data. But finding the right data is a challenge in itself.
Garbage in, garbage out, as they say.
Exactly. And Winn emphasizes that model development is iterative, rarely perfect on the first try.
Build, test, refine, repeat.
You got it. Start simple, test against your data, see where it falls short, then tweak it.
Maybe add variables, change assumptions, even try a different algorithm.
Until you find that sweet spot, accuracy, complexity, interpretability. Gotta balance them all.
And Winn reminds us to evaluate throughout.
Crucial. Gotta see how it performs not just on the training baby, but on new stuff too.
Like a pop quiz for the model.
Exactly. There are tons of metrics for this, from simple accuracy scores to more sophisticated ones.
Like precision, recall, AUC. Pick the right one for your goal.
Speaking of right tools, Winn's a big advocate for visualization too.
Yeah. They're not just about making things pretty. They can really reveal hidden patterns.
Show you where the model needs improvement, and to Z, help communicate your findings. Builds trust, too. You can see how the model's making decisions, spot potential problems.
Okay, let's take a step back. We've covered a lot in this deep dive, from solving murders to predicting game outcomes and even filtering email.
We've learned about all sorts of tools and techniques. Probabilistic programming, graphical modeling, even how to harness the crowd's wisdom.
But the big takeaway for me is model-based thinking. It's a different way of approaching problems.
Absolutely. It's a probabilistic mindset. You acknowledge uncertainty, you build models that capture the system's essence.
Not just rules and predictions, it's embracing complexity, finding the WHY behind the patterns.
And it applies far beyond the examples we talked about. It's a framework for any field.
So as we wrap up, I'm feeling excited. Model-based machine learning, it's not just about algorithms.
No, it's about a new way of thinking.
Curiosity, questioning assumptions, that thirst for deeper understanding.
The world is full of uncertainty, and those valuable insights, often hidden. It takes careful observation, thoughtful modeling, a bit of probabilistic thinking. That's how we unlock them.
So, to our fellow deep divers out there, keep exploring, keep questioning, keep building those models. Until next time.